Okay, before I start, let me ask you one thing. I've been saying things like SU2 and SO3 are homomorphic. Is that something which everybody knows? I assume that it was something which everybody knows, but do you know, for example, what the homomorphism is? Or one possible homomorphism? Yes or no?
No, sir.
Okay, then I think rather than deal with the abstract stuff, which we will have to in the long run, it's perhaps a better idea to do the concrete things at the beginning. So what I will do is something like this. I've already talked about SO3 the other day. At least I've talked about the manifold structure of SO3, what kind of set it is, and talked about the topology of the set to some extent. I've also made statements like SU2 is homomorphic to SO3 and it is simply connected and so on. But I think it's important that you actually explore the direct connection, the concrete connections between the two. So I will actually take a break from what I've been discussing so far. I've been discussing the basic structure of all Lie algebras, and in particular semi-simple Lie algebras. I've been trying to get there, but that will have to wait a while. I will talk about the more concrete things like SU2 and perhaps even SU3 before we go on to the general theory. Two reasons for that. The general theory is rather abstract. So seeing the concrete thing first might make it easier to follow what we are trying to do in the general theory. Also, well, just in case I don't have enough time to complete everything, SU2 and SU3 are things that you have to sort of take home anyway as direct physically important things. So let's do it that way. Some of this will be a repeat basically because much of SU2 theory I've already done in the guise of angular momentum algebra. So I might jump around some of those steps, but let's do the concrete thing first, and then we will, once we have the concrete thing under our belt, then we will do the theory of Lie algebra, at least semi-simple Lie algebras in general, and there you will see many of the structures that we will see here get reflected in a more general setting. So first, this SU3, SO2, SO3, SU2 homomorphism. But even before that, let me just give you a quick reminder of why we want the SO3 group, want to talk about that at all. This is the group of all rotations. And I hope everybody knows why rotations are represented by SO3 matrices. Yes, no, whatever. If yes, say yes. If no, say no. If you say nothing, then I'm getting scared once again that I'm not connected. I still am connected, I guess. So, the fact that the rotation group is the group of special orthogonal 3x3 matrices. Of course, I may say that as a statement, but do you know why? The statement is, of course, not what we are after here. Right?
I know, sir.
Sorry, I couldn't hear you. You know that, right? Or yes or no?
No.
No. Okay.
Sir?
Yeah.
Do they represent like doing one operation after the other, like that is embodied in the SO3? That's why
that's a group, but why is it a 3x3? Why is it specifically 3x3 orthogonal special matrices? So that was the question. Why SO3? Why not something else? SO3 specifically is a mathematical structure which has 3 by 3 orthogonal matrices as elements. And S means special, determinant 1. Why specifically that? Now, unfortunately, I assume that you know all of this because, okay, did I teach you quantum mechanics, by the way? I didn't, right?
No, sir.
Oh.
No, sir.
Okay, so much of what I'm saying is basically part of the advanced quantum mechanics course anyway, where we talk about rotations and connections with symmetries and rotations and angular momentum and stuff like that. So, of course, different teachers emphasize different aspects. So you may not have seen this done. So let me just quickly, this is very easy stuff, but it's also very, very important. And perhaps it's actually more important than, at least it's important, very important to understand the SU2 and SO3 thing, and SU2 algebra properly. And if you know the SU2 algebra properly, the theory of all semi-simple Lie algebras will sort of become easy after that. So let's start from the group itself, the rotation group. Rotation group, of course, is in a sense very easy. You just rotate your coordinate system. And if you keep on rotating, as you said, 2 rotations one after the other is the rotation. There is an identity, which is no rotation at all. Every rotation has an inverse. And rotations being transformations, all transformations are associative, so associativity is easy. So then they form that the set of actual physical rotations form a group is easy to understand. But why is that the group of 3 by 3 rotation matrices or 3 by 3 orthogonal matrices? Well, the answer is in the fact that rotation can be, of course, represented by rotation matrices, which I'm pretty sure all of you know about. Right? If you have X, which is a vector which has all 3 components X, Y, Z, I'm writing that as a column here. Under rotation of coordinates, and here we have to be clear about whether we mean active or passive rotation. Here we are talking about rotation of coordinates, which is passive. System stays the same, the coordinate system rotates. Okay? You of course also have an equivalent active version where the coordinate system stays the same, the system rotates to the opposite angle. We have to choose one, we are using the passive version. Okay? So the coordinates X, when you rotate your coordinate system, becomes a new bunch of coordinates X prime. And that, of course, is linearly related to the old bunch, and you can always write that as a matrix R times X, right? So far, any problems?
No, sir.
Okay, and of course, this R has to be a 3 by 3 matrix. There's no issue definitely about that. Question is, why is R orthogonal?
So that the norm remains invariant.
And why is it determinant 1? Okay, you are right. It's basically so that the norm remains invariant, in the sense under a rotation, this quantity X transpose X, which is really the column, the row vector XYZ multiplying the column vector XYZ. So X square plus Y square plus Z square is really a 1 by 1 matrix with entities X square plus Y square plus Z square. But even mathematicians don't distinguish between 1 by 1 matrices and numbers. At least most of them don't. Physicists definitely don't. So this is the number X square plus Y square plus Z square, which is of course the length squared of a vector. And one property of rotations, this is of course rotations about the origin, is that it does not change the length of vectors, right? So one thing must happen is X prime transpose X prime must be equal to X transpose X. By the way, if at any stage you feel that I'm going too fast, I am going to go a bit fast because much of this should already be known to you. If I just am going too fast, stop me and let me know. Now, what this actually implies, of course, is xt, rt, r, x is xtx. And what does this tell you?
R transpose R must be identity.
Okay, there is a bit of a problem with that last statement. It's right, but does this mean that whenever this, of course, for all x, for a particular x, if x transpose ax is equal to x transpose bx, that could very well happen because of numerical accident, right? For a particular x, that could always be true.
Yes.
But if this happens for all
For
x,
all.
does this mean that A equals B? Does this x transpose AX equals x transpose BX imply A equal to B? Because that is apparently what you are using here, right? Because RTR is x transpose identity x. And because this is true for all x, after all, the length of every vector has to stay the same. You are saying R transpose R is the identity. Is that what you are really saying here? Of course, it works the other way around, obviously. If RTR is the identity, then this will definitely be true, right? The implication the other way around is obvious. Similarly, if A is equal to B, then x transpose AX will be equal to x transpose BX for all x. Obvious implication. But is this true? That if x transpose AX is x transpose BX, then A equals B?
A minus bx can also be a vector orthogonal to x of t.
Why? When will that happen? Okay, what you're saying is okay, a slightly convoluted version of this, right? What we are really saying is if this is 0, does this imply that A minus B is 0? Right? What you're saying is A minus BX could end up being orthonormal to X. Then you would get a 0. For all X, remember, not for one particular X. That is, in other words, suppose I have X transpose CX is 0 if X transpose CX is 0 for all X. Is C equal to 0? If C is equal to 0, no problem. If C is equal to 0, X transpose CX is 0. Does it work this way? If C equal to 0 means is C necessarily equal to 0, right? That's what I'm asking. Any ideas? Hint. What kind of object is this? Is this a number, a matrix, or a column vector, or what? X transpose CX?
It's a number.
It's a number.
Number, right? We are assuming the C is a 3 by 3 matrix or n by n matrix in general. This is a number. Okay, what happens when you transpose a number? It's also a 1 by 1 matrix, right? So when you say transpose, you're actually transposing the 1 by 1 matrix. What happens to it?
It stays the same. Yeah.
What happens to XTCX when you transpose it?
XC transpose X.
XT?
C transpose.
C transpose X, right?
Yeah.
But these two have to be equal to each other? Always?
Yes.
Because they are 1 by 1 matrices, right? Transposing doesn't change anything. So, one thing you can immediately see, if C is antisymmetric, then this number will become its own negative. Is that clear?
Yes.
So if C is antisymmetric, so it is not necessarily 0, C is antisymmetric. By the way, even this logic is not finished, not correct, not precise at this stage. Because all we have shown is if C is antisymmetric, then X transpose CX will vanish. So you don't need 0. Antisymmetric matrix will do. So for example, here, if A had been A plus B, A equal to B plus C, where C is antisymmetric, this will definitely work. right? Is that okay?
Yes, sir.
So question is, does it actually work both ways? That is, C is antisymmetric definitely implies X transpose Cx is 0. I'm asking the opposite question. If X transpose Cx is 0, are you sure that C is antisymmetric? For all X, again. Can you think of the answer is actually it is antisymmetric. It has to be antisymmetric. 0, by the way, is antisymmetric. So that's covered. Why does it have to be? How would you prove that? Well, the simplest way to prove that would be just to take specific x's, right? This is true for all x, right? So take x equal to 1, x equal to 1, 0, 0. So this becomes 1, 0, 0. Then whatever this C matrix is, then 1, 0, 0. Was a number. So you have C11, C12, C13, and so on, right? And anybody tell me what this number is?
C11.
C11. So we get C11 is 0, right? That much is easy. What about C22? How would you prove that that is 0?
Take 0, 1, 0.
Exactly. And x 0, 0, 0, 1 will easily prove C33 is 0. Straightforward. So at least we are making some progress, right? You know that in an antisymmetric matrix, the diagonal elements have to be 0. And we have just established that. But what I need to do is show that C12 plus C21 is 0, right? Things like that. How would I show that? Not only that, I have to show C13 plus C31 is 0, C23 plus C32 is 0. In general, Cij plus Cji is 0 if there were more values for I and j to take. You had larger matrices. Here you have only 3 by 3, but anyway, its result actually works for n by n. So what would you choose? A very simple option. Just choose 1, 1, 0 and check. Now, if it's 1, 1, 0, you need this element and this element after the multiplication, right? You don't bother about this. But if you're doing this element, what you're going to get is, if it's 1, 1, 0, and although you already know that this is 0, right? When you do this multiplication, what do you get? You get just C12 here. Is that okay? First row.
Yes.
And the second row, what do you get? You get just C21. And then you get 0. Right?
Right.
And then I don't even care what you get here, because that's going to not contribute. You get C12 plus C21. Since X transpose Cx is 0 for all all X is 0 for this one, so it tells you C12 equals minus C21. In fact, all you have to do is take an X with the 1 in the ith position, 1 in the jth position, zeros everywhere else. And if you do that, you're going to get that the value of X transpose Cx is Cij plus Cji, and that has to be 0. So let's go back to what we were saying. Basically, the problem was you identified R transpose R with the identity because X transpose of R transpose R, X is the same as X transpose identity X. What we have shown right now is if these two things are equal, then A does not have to be equal to B. A and B could differ by an antisymmetric matrix. In other words, you can only make a statement about the symmetric part of A. If this is true, then the symmetric part of A must be equal to symmetric part of B. I hope everybody knows what a symmetric part of a matrix, of a square matrix is, right?
Yes, sir.
So symmetric parts must match. The antisymmetric parts of A and B could be anything. In particular, could be very different, because the antisymmetric parts don't contribute to these quadratic forms. There's a formal name for this kind of thing. It's called a quadratic form. And the antisymmetric part simply does not contribute. Okay? So what do you have here? What you have is X transpose RTR X. The reason why I'm emphasizing this so much is arguments like this will be very important in more complicated situations too. Here, all you can really conclude is RTR symmetric part and identity symmetric part have to be the same. Okay? But I'm claiming that that actually means that RTR is the same as I. Why? Because I is already symmetric, so there's nothing to, the symmetric part is itself, right? And what about RTR?
It's also symmetrical.
It's also symmetric because if you take its transpose, it gives you the same thing back. It gives you R transpose R again, right? AB transpose is B transpose A transpose. So transposing this gives you back this. So this is actually correct. I was not disputing the conclusion you drew. I was just pointing out that there was an additional piece of argument to be made here. RTR equals identity because both of them are symmetric. If that had not been known, you could have said that the matrix on the left equals the matrix on the right, just because the quadratic forms match. Okay? So first part, a rotation matrix is orthogonal. Done. What about determinant 1? So we know it's a member of O3. It's a 3 by 3 matrix. It's an orthogonal matrix. How do you know it's SO3? Okay, what do you know about determinants of the matrix already?
Determinant is 1 of a rotation
Why?
matrix.
Why? Well, that's a statement. Why is that true?
Because rotations don't increase or decrease area, so the Jacobian is 1.
Close, actually, but you should realize that that's, okay, it's really not area so much, it's volume. It's in 3D, it's actually volume that you're talking about, but you're right. It doesn't increase or decrease volume, it keeps the volume the same. But the volume changes by modulus of the determinant, not by the determinant itself. In fact, very equivalent to what you said right now is this algebraic calculation. This has to be, what is this? Determinant of R transpose R? How much is this?
1.
Has to be because it's determinant of the identity, but this is actually determinant of R transpose times determinant of identity, right? And R transpose and R have the same determinant, so it is determinant of R whole square. That alone would have told you determinant of R is either +1 or -1. Note, O3 has two kinds of matrices, those with determinant +1 and those with determinant -1. How do you, yeah.
We are considering real values, right? That's why we got
this is orthogonal transpose.
okay.
This is not an not Hermitian adjoint. And these are real numbers. After all, this is a real bunch of 3 coordinates which is transforming to another bunch of 3 real coordinates. RIGs are all real. All the components are real.
Yes.
So yes. But when you square something and get 1, the only possibility is, of course, that number, even if it had been complex, ab initio, would have to be either +1 or -1, right? Even in the complex plane, +1 has only these 2 square roots, or only these 2 numbers squared to 1, to be more precise. Okay? Right? So we already knew that an O3 matrix, an orthogonal 3 by 3 matrix, would have a determinant of either +1 or -1. How do you argue that rotation matrices must have a determinant of +1 and not -1? For that, what we did yesterday, or the last day rather, would be useful. Remember this structure? The SO3 group, actually I kept on calling it SO3, but I meant rotations. The group of all rotations can be parameterized by this vector of length bounded by pi with identification of diametrically opposite points. Right? The one important thing about it, okay, where is the null and where is the zero rotation here? Identity rotation. Identity of this group is, of course, no rotation at all. That means identity. Where on this picture would the identity be? Let me remind you once again that in this picture or in this equivalent structure,
Hello. So you're not audible.
hello?
Hello.
Go ahead. Tell me. Where is the identity in this whole thing?
Should be at the center.
Exactly. Because the vectors are basically axis and angle, right? The center has zero length, zero angle. Okay, now take any rotation. Any rotation will be a point somewhere here. Could be the points on the surface are a bit special, but that's also any point on the surface would actually talk about rotation, right? Specific rotations to 180 degrees. But any other rotations would be inside. Right? Take any point. Let's say this point, this red point here. Can I imagine that I'm joining this red point to the center with a line. So you can, of course, continuously move from the center until you hit this point. Agreed? Hold on.
Sir?
Yeah.
Can we say that one rotation after the another comprises of another rotations, and if we multiply the determinant of -1, it will become +1?
Yeah, but so it could very well be that some determinants are -1, some determinants are -1, +1.
Okay.
Of course, your argument is not really bad. You could actually argue that you could get every rotation you could get by, so a rotation through this kind of rotation, Rn theta, will always be Rn theta by 2 squared, right? Okay. Every rotation, that's actually a good argument. But not the way you were talking about, it's the other way. If you say Rn theta is always the product of Rn theta by 2 twice. Yes?
Yes, sir.
And can you see why this implies that Rn theta has to have determinant 1? Because this
negative
means
in r n theta by 2.
the determinant of r n theta would have to be the square of this determinant, right?
Yes.
And although the determinant of r n theta by 2 we have proven could be either +1 or -1, if you square it, then this number has to be +1. And therefore determinant of r n theta has to be +1. You're right. That's one argument. In fact, this argument is essentially the same, except that it's a bit more sophisticated. The argument I was trying to give you is a bit more sophisticated, and it sounds a bit more sophisticated. But if you think about it a bit, it's essentially the same argument. Here, all I'm saying is if I can join the origin, which of course, remember, is the zero rotation. That means has the identity matrix here, 1 0 0 0 1 0 0 0 1. And you can join it with any rotation, any of your rotation r n hat theta to that identity with a straight line. What does it mean? It means I can keep on moving along this straight line. And if I do, the straight line is just for convenience. Any curve would have done. But you can always join with a straight line, and straight line is easier to think about. You're keeping the axis the same. You're keeping on changing the angle very, very slightly until the angle becomes theta. Right? As you move along this curve, you started with the identity matrix. By the time you get here, the angle changes slowly, slowly, slowly until it becomes theta. Right?
Yes.
So the rotation matrices change continuously from identity to this value. So every R is connected continuously to I. Now, connected continuously does not have to be along the straight line, could be along this curve, but still connected continuously. What that means, okay, now what does this mean about the determinant? The determinant is a function of R, right? The matrix. It actually is a function of the elements of the matrix, and it's a continuous function of the elements, right? How do you form a determinant? You multiply elements together, you add them, subtract them, and so on. Right? So all of these are continuous operations. So if the elements of a matrix changes continuously, then determinant R has to change. If it changes, has to change continuously. You agree?
Yes, sir.
But it started out at +1, right? Now, it has only two allowed values, +1 and -1. Okay. Since det R was 1 at identity, when it's of R, you have had identity, and det is continuous, it can not change. This is a topological argument, which essentially all topological arguments are like. You are saying, or most topological, not all, but most topological arguments that of conserved quantities in physics, they're essentially like this. The allowed values of det R is discrete. The allowed values is discrete, right? Are discrete, right? Only 1 or -1. If the allowed value had been any number between 1 and -1, then starting at 1, it could have slowly changed and got to -1 anyway, right? However, if the allowed values are only +1 and -1, it's impossible for +1 to change to -1 unless it jumps somewhere. And jumps are not allowed. It's a continuous function.
Sir?
Yeah.
From the previous thing that we wrote, that determinant of r n theta can be decomposed into square of r n theta by 2. So since the group is continuous, can't we say that for every rotation matrix, you can write this as a square of determinant of some other matrix?
Yeah,
So
that's
since it is square,
okay,
it has to be positive.
That's exactly what I said, right? I said that this is a perfectly good argument. Not the other way down, not that two rotations make a rotation, but every rotation is actually composed of two half rotations.
Yes, so every rotation can be decomposed like that.
Exactly.
So it has to have
Exactly,
plus
but
1.
this argument that I'm giving you sounds a bit more sophisticated, invokes larger words like topologically conserved quantities or so on. And basically, it's the same argument here. Note that just because that's like you could make it up to 2 halves, you could make it out of 10 1/10s, or 1,000 1,000s, or 1,000,000 1,000,000s, and so on. And so basically what you are saying is you can slowly change until you get here. And because the matrix components are not constrained to have discrete values, right? They can continuously change from 1, 0, 0 to other values. But determinant, because it's constrained to have only +1 and -1 as possible values, it cannot change to any value in between. If it starts at +1, it stays at -1. I'm not saying that this argument is wrong. I said that it's okay. This will work. This is just an alternative argument, which actually is also very useful because it's used. It can be used in other places where such simple arguments don't work out. And it's basically saying that if a quantity can only change continuously, and its only allowed values are discrete, then it cannot change at all. That actually is behind all quantities which are called topological conservation quantities, and so on. Okay, so something very much more advanced can also be sort of put in here. But ultimate upshot is, of course, the same, that R is 3 by 3, orthogonal, and that R is 1. Which is why all R's together form SO3, special orthogonal 3 by 3 matrices, the group formed by that. O3 actually, well, SO3 is a normal subgroup of O3. You can easily check that. Okay, proof of this is trivial. Can anybody give that proof to me right now? How do you prove something is a normal subgroup? You take any element from O3, let's call that X. Take an SO3 element, let's call that Y, and form XY X inverse. If this thing is an SO3 element always, then SO3 is a normal group. And you see why that's true?
Take the determinant.
Of course, take the determinant. I don't care what the determinant of X is. Actually, SO3 is a normal subgroup not only of O3, SO3 is a normal subgroup of GL3. Take any group, any invertible matrix, form XY X inverse. If Y is determinant 1, XY X inverse will also be determinant 1. Right? So SO3 is invariant under this conjugation operation for every element in O3, even every element in GL3, and O3 by SO3. Now O3 is an infinite group, SO3 is an infinite group. But can anybody tell me how many elements this will have? In fact, what is this O3 by SO3? It's first of all a set where the elements are equivalence classes. Every SO3 element is in one place, right? Is one of these equivalence classes just SO3? The others are cosets of SO3. How many cosets can SO3 have in O3? That's the question. What are O3 elements? 3 by 3 orthogonal matrices. What are SO3 elements? 3 by 3 orthogonal matrices with determinant plus 1.
So cosets will have, there will be two cosets. One with determinant plus 1.
Exactly. There will be all the matrices with determinant plus 1 will be one coset, which is SO3 itself. The other one, which is not a group, will be all orthogonal matrices with determinant -1. But you all know what they are, right? What are those?
Reflections.
They are reflections or combinations of or inversion.
Rotation reflection.
But that's actually Okay, reflection. Reflections or rotation reflections? Or more simply, inversion and rotation inversion. A reflection is also a rotation inversion, always, right? And this, so there are two elements, and this is basically Z2, it's the group 1 minus 1. Effectively, one. So you have two cosets, and one of the cosets can be mapped to the number 1, the other coset to the can be mapped to the number -1, which are the determinants, of course. And this mapping will work fine. Is it okay?
Yes, sir.
Okay, great. So this is all about SO3, the group. Now, before we go on to talk about SO3, the algebra, which is essentially take a look at what happens for very close to the identity, let me just first show you the connection between SU2 and SO3. SU2, of course, are 2 by 2, unitary, special matrix. Special means determinant 1. Okay? That such matrices form a group is very easy to show. What we want to show is that there is a homomorphism between SU2 and SO3. That is, for every SU2 element, there is a unique rotation matrix. And this connection between unitary matrix and rotation matrix obeys the group composition law. If U1 corresponds to R1 and U2 to R2, then U1, U2 corresponds to R1, R2. Now, I'm pretty sure you may even know this. You may have seen this somewhere. First of all, rotation matrices act on X, Y, Z, or let's say things like R vector. Now, this object should be a perimeter object, right? And it's got two faces. What kind of an object is this? Yes?
Matrix.
Yes, sir? Matrix. What kind of matrix? It's a matrix. But what kind of matrix? Size first. What's the size of the matrix? This should be sort of elementary to everybody, right?
It's 2 by 2.
It's 2 by 2. Okay. What now 2 by 2? What are the characteristics of 2 by 2? Does it have? It's a 2 by 2 matrix. Then what kind of 2 by 2 matrix?
Hermitian.
Hermitian. Great. Because all the sigma matrices are Hermitian. Anything else? Any other property? Any other special property which all the sigmas have and which is preserved by linear combination?
Determinant is 1.
That's not preserved by linear combinations. Adding to matrices, right here, first of all, even sigma 1 x, that doesn't have the determinant x. Right? And by the way, none of the matrices have determinant. Sigma 1 doesn't have determinant +1, right? What is the determinant of sigma 1, sigma 2, sigma 3? Remember the matrices? What is sigma 1? By the way, tell me. Tell me the matrix. You know this, right?
0, 1, 1, 0.
Good. 0, 1, 1, 0. Determinant?
-1.
Sigma 2?
0 minus I, 0.
Determinant?
-1.
Sigma 3 is the easiest of the lot, but it's also determinant -1. So none of these are determinant 1.
-1, yes.
And sigma 1 x doesn't have determinant -1. Come on, that's not true, right? In fact, what is the sigma 1 x plus, so you can see is clearly z minus z x minus I by x plus I by. The determinant of this matrix is actually going to play a very important role soon. But right now, I'm more interested in what is the common property of all such matrices, which not a specific one to a particular matrix. Another thing that you can see which survives linear combination, does not change when you linear combine, is trace. Trace? Sorry. Hello? Yes? Yeah, I'm speaking. Trace does not survive linear combination, but tracelessness does. Right? Even every matrix of this form is z minus z x plus minus I by x plus I by. Hermitian 2 by 2 traceless. Okay? By the way, the converse also works. Every Hermitian 2 by 2 traceless matrix, how can they write that down? You can write that as alpha minus alpha, traceless. Diagonal elements have to be real and negative of each other. What about the off-diagonal elements? They have to be complex conjugate. So if this is beta minus I gamma, where alpha, beta, and gamma are all positive, all real numbers, alpha, beta, gamma are real. Right? Where A vector has elements alpha, beta, gamma. Is that clear? Sigma dot R is a 2 by 2 Hermitian traceless matrix. Not only that, every traceless Hermitian matrix has to have the same form. Has to be sigma dot R prime for some R prime. Is it okay? Yes? Yes? No? Tell me.
So why are we dealing with sigma matrices? Like, do they form a representation or something?
Well, that was true, but right now that's not what we are looking at. We are looking for a homomorphism between, which will allow us to connect a unitary transform 2 by 2 unitary matrix to a rotation, which is, you'll soon see why sigma matrices, but is this much okay? That sigma dot R is a 2 by 2 Hermitian traceless matrix, you all agree to that. Are you also sure that every 2 by 2 Hermitian traceless matrix will be of this form?
No, identity won't be of this form.
Really? Isn't it? Is identity a 2 by 2 Hermitian traceless matrix?
Oh, it's not traceless. Sorry, my bad.
Good. Identity will not be of this form. You're right. But identity is not here. Not sigma, not Hermitian traceless. Now let's think about this. Let's start with sigma dot. And okay, there's another thing that I want you to focus on is what is the determinant of this?
Minus z square, negative x square plus y square plus z square.
Right. So essentially the square of the length of the vector r except for a minus sign. Okay. Now realize this. I want to talk of rotations which will change r to r prime. Okay. Right? But sigma dot r and sigma dot r prime, which is sigma dot r acting on r prime, these two share some important properties. This is 2 by 2. This is of course also 2 by 2. This is Hermitian. So is this. This is traceless. So is this. And because you're carrying out a rotation which does not change the length, this R and R, sorry, I made a mistake. This is not R prime. The R acting on R. Capital R, the rotation acting on R gives you R prime. And since the determinant of this must be equal to the determinant of that, right? Is it okay? If R prime is a rotated version of the vector R through some rotation matrix capital R, then sigma dot R prime and sigma dot R are both 2 by 2 traces Hermitian, of course, but they also share the same determinant. Do you all agree? Yes? No, tell me something. Do you agree? Yes or no?
Yes.
But can you think of a way of this is a 2 by 2 traceless Hermitian matrix with a given determinant? What can you do to such a matrix that is stays Hermitian, stays traceless, stays determinant, stays same in determinant?
Unitary transformation.
Good. Take any unitary matrix and form this. U dagger, of course, is the same as U inverse. Any unitary. U is a unitary matrix. Of course, it has to be 2 by 2. If you do that, trace doesn't change. First 0 stays 0 because that happens under all similarity transformations. Determinant doesn't change because that also doesn't change under similarity transformation. And Hermitianity, of course, that would be true for any similarity transformation, right? I could have taken any non-singular matrix A and formed this. The trace and the determinant would not have changed. But I cannot do this with any arbitrary matrix, arbitrary invertible matrix. Why? Because I also want the thing to remain Hermitian. That will happen only, sigma dot R is Hermitian. That will happen only if the unitary transformation also is a transformation. If this similar transformation is actually a unitary transformation. U sigma dot R, U dagger. That is Hermitian. Is that okay?
Yes.
Great. So what have we shown? Given a U, U dagger, remember, is the same as inverse, is sigma dotted with R acting on R. And this defines your R for you. For a given U, you have a R. Okay? Remember, this is true for all small R vector. From that, you can easily, from that, okay, given this side, you can easily actually figure out what the rotation matrix is. I will leave you the task of figuring that part out. But you will all agree that this U defines the rotation?
Yes, sir.
Question is this a homomorphism? So if U1 maps to R1 and U2 maps to R2, does U1, U2 map to R1, R2? The answer is check. U1, U2 would map to this.
Sir,
Yeah.
how did you get the above equation expression?
I was saying exactly what I did so far. All I'm saying is, if this U is a unitary matrix, then if you did this, you're going to get a 2 by 2 Hermitian traceless matrix with the same determinant as sigma dot R to begin with. So it will of course be of the form sigma dot R prime, where R prime has exactly the same length as R, which I'm calling rotation matrix R acting on small r.
Oh, is it because the determinant is preserved, like x square plus y
Yeah.
square?
Well, not only determinant, all of them. Tracelessness is preserved, so that is why it's of the form sigma dot. Hermitianity tracelessness is preserved. That's why it's of the form sigma dot R at all. Right?
Yes, yes. Okay, got it.
So 2 by 2 Hermitian traceless determinant, all of them have to be preserved. And here, so what is this thing in the bracket here? As U1 sigma dot R2 acting on R, U1 dagger. Oops. And then this is sigma dot R1 acting on R2 R. Right? So U1, if U1 corresponds to U2, sorry, if R1, R2 is equal to R3, then U1, U2 corresponds to U3, which is basically linked to R3. Got it? So this is homomorphism. U1 gives you R1, U2 gives you R2, U1, U2 actually gives you R1, R2. Right? So, okay, we have not shown that. We have shown U2. Haven't we? Any questions about this part, this much so far? Now, okay, any doubts about this? There should be one.
So I'm worried about onto condition.
Great. Well, many people would say U2 is homomorphic to SO3 simply because U1, U2 corresponds to R1. Right? Group product is preserved. That's, remember, I talked about this. Definition of homomorphism changes from author to author. Some people say homomorphism is just group order preservation, the group multiplication preservation. That's all you need. Others insist that it has to be an onto map. Okay. So, can you figure out why you can always find a U for every R? That's the question. There was a gap. Our definition of homomorphism, that is the one we have used, which makes statements of some of the theorems much easier, is that homomorphism map also has to be onto. Which means every rotation matrix has to have a corresponding U. Here we have shown that U corresponds to R. That's fine. How do you show that every rotation matrix corresponds to some U or the other? Yes? Now that part, I will let you worry about this. This is an important question, but I will give you a hint. The hint is basically in a topological kind of argument. The answer is the fact that every rotation can be reached from the origin in tiny pieces, that should give you a way of doing this. You are proving that is also onto. I will not say any more. You try to figure that out. But this is U2, right? Not SU2. Now, why is it not an isomorphism but just a homomorphism? Can anybody tell me that? Yes, can you think of more than one unitary matrix which will give you the same R? What happened? This is the rule, right? Basically, U sigma dot R U dagger is U sigma dot a rotation matrix R. Sorry, not U on both sides, it's just this. And this tells you what this is the R corresponding to U. Can you get the same R, that means same this side, even if you change the U to another unitary matrix?
We can get another one.
Which one?
Like the one, it doesn't change the determinant, right?
It's not a question of determinant. You need to get exactly this matrix. That the determinant did not change just tells you it's a rotation. But I'm saying the same rotation. How do you get the same rotation? By getting exactly the same value. Can you change U and get exactly the same value? It's usually pretty easy to figure that out. One other, if a given U does the job, does any other unitary matrix also do the job?
Inverse of U?
Inverse of U will usually definitely not do that job. You actually, hopefully, because this is a homomorphism, if U maps to R, U inverse should map to R inverse. It will definitely give you a different result.
Right.
Any scalar multiple of U?
Great, but any scalar multiple of U will do.
Other than 0.
No, but suppose I multiply U by C. What happens to U dagger?
Becomes 1 by C U.
Does it? Why does U dagger become 1 by C U dagger?
U dagger is U inverse, right? So
Okay. This is where you have to be careful about your logic. U was a unitary matrix. So U dagger was U inverse. Are you sure that C times U is also a unitary matrix?
It's C U dagger.
No, that's more obvious. It's C star U dagger, right? Come on.
okay,
That's true for every adjoint. Okay. So this actually doesn't stay the same unless so this our aim is to keep the left hand side exactly the same, right? And also ensure as it's, if you replace U by CU, can you do that? Is CU as only unitary matrix? Multiplying a unitary matrix by a number, does it actually keep the unitary matrix, keep the resulting matrix, is the resulting matrix also unitary? I think that was what you sort of assumed when you said you would have 1 by C.
Yeah, so as long as mod C square is 1, then shouldn't.
Actually, as long as mod C square is 1, then shouldn't be a problem with this with the left hand side. And in fact, that also keeps the CU unitary. You can easily check that. That is essentially obvious from this. That is, U is if U is unitary, it is the I alpha times U is also unitary, right? And if the I alpha times U produces exactly the same result as U does. Because you have both U and U dagger, the I alpha cancels. Okay? Clear? So this homomorphism from U to this to SO3 is actually is not an isomorphism, definitely. It's an infinity to 1 map. Clear? Infinitely many different unitary matrices give you the same rotation. 2 unitary matrices differing by a phase factor will give you the same rotation. Okay? Right. And it's important to note that actually gives this unity. But can we cut down on this infinity to 1 map? Can we make it closer to being 1 to 1? Well, for that, notice the determinant of the I alpha U. Can anybody tell me what that is?
E to the power I alpha times the dimension, like raised to dimension of.
What? Can you just repeat slowly?
E to the power I alpha is a scalar.
Yeah.
That will come out with the power of the dimension.
Yeah. What is the dimension?
U is 2.
Yeah. So it is a twice I alpha. Right?
Yes.
The German changes by either twice I alpha. But another important thing about det U. Any idea about what det U can be like? U is what is the determinant? What can you say about the determinant of a unitary matrix?
Its determinant square is 1.
No. That would be incompatible with the statement. If you square by 1, then it could be either +1 or -1. But here you see this is a unitary matrix, right? We claim this. If U is unitary, the I alpha is also unitary. Trivial to do. But now it is a complex phase vector as a determinant, right?
Its mod square will be 1.
Yeah, determinant of U's mod square will be 1. Because your det of U dagger is 1. Det of U dagger is not equal to det of U. It's det of U's conjugate. The det of U always has to be a phase factor with real phi, of course. So now, if you can easily see from here that if you choose e to the minus I phi by 2 u, take any u, replace it by e to the minus I phi by 2 u. You get a unitary matrix, but a special kind of unitary matrix, right? What is that? What kind of a unitary matrix is this? What is the determinant of this?
One.
So instead of using any u, you could actually divide by the square root of its determinant and end up with a unit determinant matrix which does exactly the same job. Right? And so instead of using u2, what you can use is su2. And so instead of using all unitary matrices, just use su2 matrices. That will also work. And this homomorphism is no longer infinity to 1. Can anybody tell me how big this homomorphism is? Is it a one-to-one map? That is the unique su2 matrix. Yes? Even this should give you a very good hint. You are dividing by the square root, right? Square root of the determinant. Now this determinant is, what kind of quantity is this determinant? You're starting with a unitary matrix U, and you're dividing it by the square root of its determinant. But the determinant is e to the I phi. Doesn't that tell you something? How many square roots does it have?
2. So
Yeah, and so there will actually be two possibilities here. If U works, look, earlier you said if U works, it is the I alpha U also works, right? That's what you said before, or we said before. Now, this was okay because we were talking about unitary matrices. If U is unitary, it is the I alpha U will also be unitary. But now that we are specializing into SU2 matrices, if U is unitary, if U is special unitary, the I alpha U in general will not be special unitary. But it will be special unitary for one non-trivial case. Which one is that? And in a non-trivial, I mean, of course, if the I alpha is 1, is a trivial case. That means U is the same U that you're talking about. But what's the other one? And the answer is also obvious from the fact that this is the way you constructed it. Divided by the square root of the determinant. Yes? Come on.
Multiples of pi.
Well,
The alpha.
yeah, that's the as far as U is concerned, what? Either U and minus U. Minus U is also a SU2 matrix. If U is a SU2 matrix, so is minus U. Is that okay? Yes?
Yes, right.
And they produce exactly the same effect. So this map is a 2-to-1 map. There are two SU2 matrices corresponding to every rotation matrix. It's a homomorphism. U1, U2 corresponds to R1, R2. For every U, there's a unique R, but it doesn't work the other way around. For every R, there are two U matrices. If U works, minus U also works. Okay, which is why, because of that, SU2 is not isomorphic to SO3, and so they are really not the same group, but very, very close. Okay? And close to the identity, they both behave the same way, which is why they have the same Lie algebra, at least same real Lie algebra. Okay. Any question about this? There is just one way of constructing the SU2 to SO3 homomorphism, but I hope you are convinced that this is the homomorphism. It obeys U1, U2 is the same, it corresponds to R1, R2. And that instead of using unitary matrices, you could use SO2. You could use SU2, special unitary. And that actually cuts down on this multiple things mapping to the same thing by a lot. Not entirely, you still have a 2 by 2 to 1 mapping. Okay? Okay, before I go anywhere else, this thing, sigma dot R, this is x3 minus x3. This is the form, right? And its determinant is actually equal to negative square, negative of the length square, which is preserved under rotations. Two quick questions. One is the negative square of the length is preserved also under reflections. So how do you know that this is not a reflection? How do you know this is a rotation? Number one. Okay, number two is, okay, number two actually we have already talked about. Number two is, I have not told you the answer to that. Number two is, how do you know all rotations can be obtained this way? That is, how do you know the map is onto, which is a bit more non-trivial, but it's essentially the same kind of argument. But let me just point out one more rather fascinating thing. If in addition to sigma 1, sigma 2, sigma 3, you put in a sigma 0, and sigma 0, okay, what should the sigma 0 be? What would you call sigma 0? Sigma 1, sigma 2, sigma 3 already. Which 2 by, of course, has to be a 2 by 2 matrix. Which 2 by 2 matrix would you call sigma 0? I'm asking you to guess.
All zeros.
All zeros would, because I'm going to look, sigma dot R is a linear combination of the sigmas, right? If I want to add one more matrix which is completely null, and adding linearly combining that will not change anything. So it will, you can just might as well drop it. But can you think of any other matrix which is missing from this set? Sigma 1, sigma 2, sigma 3 actually produces a nice basis for Hermitian matrices, almost a basis for the vector space of all 2 by 2 Hermitian matrices, but not quite because of the traceless constraint, right? What are the most obvious or what are the most general possible Hermitian matrix? Tell me that. First of all, these two elements have to be complex conjugates of each other. So if this is x1 minus ix2, this will be x1 plus ix2. What about the diagonal elements?
They must be real.
They must be real. And any two, and there may be two real numbers, not necessarily negatives of each other. Now you're not imposing tracelessness. But any real number, any two real numbers can always be written this way. Right? So does that suggest to you what your what x0 goes with sigma 0, just like x1, x2, x3 goes with sigma 1, sigma 2, sigma 3?
Sigma 0 must be identity.
Yeah. Then if you take identity, this must be means you take identity this formula sigma mu x mu, which looks like a relativistic formula now. Just because I've put in the mu upstairs and you have 0, 1, 2, 3. But it's actually there's more to this as far as relativity is concerned.
Why are we introducing this sigma 0?
Because now I want to talk of only Hermitian matrices, not just traceless Hermitian matrices.
Okay, so if it has trace, then there's no problem with that.
If it has trace, then x0 will be 0. That's it.
Okay.
But now notice one thing. This matrix was the determinant of this.
x0 square minus the x1 square, x2 square.
Does that remind you of something?
The Minkowski metric.
Minkowski.
Well, not the Minkowski metric, but the invariant under Lorentz transformations. Right?
Yes.
Okay. So, just like we argued that this u sigma dot r u dagger gave you a new r which had the same determinant, same length, right? Because the determinant didn't change. Here, the determinant is basically the invariant that you want to keep invariant under a Lorentz transformation. So, I'm actually showing you how to think about Lorentz transformations along the same lines. So, sigma, you could start with sigma mu x mu, did some transformation to it so that you change it to sigma mu x prime mu, where x prime, but I want this x mu to x prime mu to be a Lorentz transformation, which means I want it to preserve the overall length. There is this 4-dimensional length, x0 square, which is the determinant of the matrix. So what do I want now? I want it to be Hermitian. Sigma, in order to be able to write it this way, I want it to be Hermitian to write it. But in order to keep in order that it fits the Lorentz transformation prescription, I want to have its determinant the same as its determinant. Can you now suggest what kind of transformation you would look at? Keeps a Hermitian thing a Hermitian thing. Okay? And keeps its determinant unchanged. What can you do? Come on, you've already seen what you can do. You want to preserve the quality of Hermitianity, and you want to preserve the quality of value of the determinant.
Some unitary transformation.
Unitary transformations would work, except for one nasty thing. Unitary transformations, of course, would work, but unitary transformations also have this problem that unitary transformations being similarly transformations will actually preserve not only the determinant, but also what? What else does a similar transformation preserve?
Trace.
Trace. And what's the trace of this matrix?
2x0.
2x0. Now, why is that? Why is it bad that we preserve this?
That must change when we
Oh,
change.
that doesn't have to change. But if you do this, if you do the unitary transformation, all you are getting are Lorentz transformations which do not change the time. And what are they? Lorentz transformations which do not change the time. What are they?
Rotations.
Rotations. Which is something you already knew. Look, earlier when we talked about rotations, we worked only with traceless Hermitian matrices because we were not bothered about changing. We didn't want to change the time anyway. Now we have introduced the time coordinate and we want to talk of all Lorentz transformations. Then the unitary transformation will simply not work. It will work, but it will not work in giving you anything new. It will just give you the rotations back. But you already knew that. Unitary U2 was actually essentially homomorphic to SO3. We have already seen that. If it was also homomorphic to SL2 to this SO31, the Lorentz group, then things would be really rather strange, right? You know that rotations are not the same thing as rotations are not homomorphic to Lorentz transformations, right? There is some. So, any further ideas? Think of what you want to keep intact. You want to keep Hermitianity intact. If instead of U, you did this, where L were any 2 by 2 matrix, will the result still be Hermitian?
Yes.
Good. But this will, in general, change the determinant, right?
Right.
How can you keep the determinant unchanged?
If mod square of determinant L is 1, then
Right.
it will not change.
If
But
L is
but
orthogonal,
orthogonal, meaning L dagger is the, do you mean L dagger is the same as L, or L dagger is the same as L transpose is the same as L? You mean orthogonal or Hermitian?
I think yeah, I meant Hermitian actually.
Well, Hermitian will it work? Orthogonal would be equivalent would be not orthogonal would be unitary, right? But you have already ruled out unitary. Well, the simplest thing, you're right, that you could just choose an L whose determinant is a pure phase, right? Is that okay?
Yes, sir.
But then you should realize that L and e to the I phi L will produce exactly the same transformation.
Right.
So again, infinity to 1. So why don't you take the simplest possibility? Take get L to be 1. Okay.
Okay.
And that actually is the group. This is basically L has to come from a group. The group is that of 2 by 2 matrices, complex valued matrices with unit determinant. That is SL2C. Special linear group in 2 dimensions, complex value. Okay? Right?
Right.
And this is homomorphic to SO31. In fact, again, it's actually 2-to-1 mapping because L and minus L will give the same result. Okay? So the Lorentz group also is a pretty simple 2-dimensional 2 by 2 matrix group, which is homomorphic to, which controls its features. Okay? So the same construction actually works also for Lorentz. And today, I will take some, okay, half an hour. I have half an hour, so I will take the half an hour to talk about how to derive the commutation relation. Have you done this before? How do you derive the commutation relations of the angular momentum group? Of the angular momentum, how do you derive the angular momentum commutation relations? Starting from the rotation group. Have you done this?
No, sir.
You have, of course, taken special things like you have taken R cross P as L, right? You have definitely done
Yes,
this,
sir.
right? You have taken
Yes.
R cross P as L and then found the commutation relations
Yes.
with L1, L2 is whatever that is, and so on.
Yes, sir.
And then when you went to spin, what did you do about the commutation relations there? That was for orbital angular momentum, right? When you talk about spin, how do you find out what the spin commutation relation was? Did you at all find it out? You showed things like L1, L2, I, epsilon ijk, L3, or there could be an H cross if you put it in, right? But this was something you had proven, right?
Yes, sir.
But how did you prove S1, S2 bracket is I? Sorry, L1, L2 doesn't. That's a stupid thing to say. You shouldn't have said yes, sir. Anyway, this is IL3. What I meant was Li, Lj. Right? But when you spin, how do you get S1, S2 conjugated with IS2?
I actually forgot this. I don't know.
Okay, you forgot that. Anybody else remembers anything?
We define the spin on the polymatrices.
Yeah, you were really actually defining specific operators, specific matrices, which has this kind of commutation relation, and then you showed that the commutation relation for those specific matrices look like the angular momentum, and you work from that, right? That's what is usually done at an elementary level. But the point is, all of these commutation relations can follow immediately from the rotation group's properties. Which is why it's no surprise that spin is what? You're talking of one kind of system which responds to rotation of coordinates in a particular manner. Spin 2 would be something which responds in a different manner. Spin 1 would be something which responds in a yet different manner. So all the different possible representations of the spin group is what you're going, of the rotation group, essentially is what gives rise to different spins. But the commutation relation is independent of the particular representation that you use. And you can derive it just from the basic properties of the rotation group, which is what I want to do in the time left. I'm not going to do all the steps. I'm going to just tell you how you would approach the thing. First, one thing is very important, rotations. Okay, so if you carry out a rotation in coordinate space, now this means the description, let's stick to quantum mechanics, of a quantum state will change, right? So you had some vector, that vector could be a single function, could be a matrix value function, could be anything, right? After all, the space is an abstract vector space on which our states live. And the precise nature of that space, what kind of elements inhabit in that space, that actually depends on what kind of system you're talking about. Well, again, drawing from what quantum mechanics you already know, a spinless particle can be described by a single wave function. A spin-off particle can be described by what? The state of a spin-off particle. What do you describe it by?
Row vector 1, column vector 1, 0.
Well, column vector 1, 0 is a very specific state. The state is actually described. So you could have also said 0, 1. Why did you say that?
I thought you asked about spin up. So
No, I didn't say spin up. I'm saying spin state of a system can be actually described by two functions, which you can write as a 2×1 column vector. Okay, it's a one function describing the state of the system. It's actually two functions. right? And the two functions you actually put together in a column. For a spin 1, you would actually need 3 functions. For spin 4, 5, 9 functions, and so on. Okay? So but each of these will be vectors. That is, you could superpose them with each other to get new states. So basically, for R, there will have to be some unitary operator which acts on R, depends on R, which acts on the states. Is that okay? So every time X goes to Rx, you are rotating your coordinate system, then the state, whatever that state vector is, whatever object that is, that changes to UR acting on H. Is it okay? Now, of course, again, just like the fact that the states, the vectors which describe states depend on what kind of system you're talking about. The operators which act on those vectors again depend on what kind of Hilbert space you have. So it depends on what kind of system you're talking about. Like different systems have different URs. Yeah? Is that okay? If you are rotating your coordinate system, your description of the state changes, and it changes by some unitary operator acting on whatever state you have. That's it. What is important is this. If you carried out one rotation after another, this means do R2 first, then do R1. You should have a corresponding. So this is some rotation, R3. So there has to be U corresponding to that. Now, if you were to do this in 2 steps, instead of doing R3 in 1 step, if you're doing it as R2 first, then R1, when you did R2, the state would change to UR2 shine. Right?
Right.
Then you did R1, the UR2 shine would then change to UR1 acting on that.
Yes.
So you should have this. Yes? Or no?
Yes.
But can you see a gap in this argument? There is a gap in this argument. I'm saying start with X, you do R1, you do R2 first, you get X prime. Then you do R1 on that, you get X1 double prime. X double prime. And you could have gone from X directly to X double prime by doing this combined matrix, which you call R1, which is by applying this combined rotation, which you're calling R1. I am saying when you were using the coordinate system where X was being measured, you are shy. This was describing your state. When you carry out this rotation R2, you go to psi prime, which is UR2 acting on psi. Then you carry out the rotation R1, you go to UR1 acting on this state. And instead of doing it in 2 steps, if you had done it in 1 step, you would have gone to UR1 R2 acting on psi. So this would have been UR1 R2 acting on psi. This would have given you UR2 psi acted upon by UR1. So I'm claiming this is true. But I'm telling you that there is a gap in this argument. Can you find out what the gap is?
Is it something related to the commutation of R1 and UR2, like
No.
like the time evolution, like?
First of all, this U is not okay. Don't confuse this U with the time evolution operator. This is what happens. This is how no time is evolving here. I'm just saying that instead of using my coordinate system, if I use some other coordinate system, how would the system change? Of course, time evolution has a role to play later. That is, how would the time evolution of a system look like from a rotated system? But that is part of the fact that Hamiltonian is commutes with rotations and rotation is a symmetry. But that's a secondary question. Right now, we're just saying how you describe rotation. the state that you arrive at after doing 2 rotations must be the same no matter whether you do it in 2 steps or you do it in 1 step. That much you should agree with, right? After all, coordinate systems are artificial impositions of the real world. The numbers, the things that you use to describe those, that may depend on your coordinate system, but it should not depend on how you arrived at this coordinate system. See the components of a vector, something more familiar from classical mechanics. The components of a vector depend on the coordinate choice, right? If you change your coordinates, the components should change. There should be a transformation law. But this transformation law cannot be arbitrary because it has to reflect the fact that if R1, R2 is R3, then the combination, then whatever transformation law acts on the vectors, that has to be T1, T2 has to be T3. Right? You understand what I'm saying?
Yes, sir.
That works for classical objects perfectly. There is a gap in this argument when you come to quantum mechanics. And I've already told you what the gap is. The state of the system seen from the final coordinate system. State of the quantum system as seen in the final rotated coordinate system must be the same no matter whether you reached it from the original system by 1 step, by carrying out the rotation R1, R2, or in 2 steps, by first carrying out R2, then carrying out R1. From that, I argued that UR1, R2 has to be UR1, UR2. But don't you realize one thing? State being the same and the vector being the same does not necessarily mean the same thing.
So could you please repeat?
The state as seen from the final coordinate system has to be the same, no matter which way you do it. But a state in quantum mechanics and the state vector, they are not in one-to-one correspondence, right? Infinitely many state vectors still do the same job, don't they? Can't you change the wave function and still get the same state? Can you? Of course, when I ask can't you, I meant you can. You know, you should know that you can change the wave function and still get the same state. Come on. That's sort of trivial, isn't it? You have known it from the beginning of quantum mechanics. So it's nothing new. Yes? Come on. Can't you change the wave function by multiplying it by a phase factor and still have the same wave function? Same state?
Oh, yes. Oh, in this sense, you mean, okay, yes.
And so the vectors can be multiplied by a phase factor, right?
Right.
So this could very well be possible. A delta could depend on R1, R2. Is that okay?
Yes, sir.
Right. And this kind of thing, if this delta had not been there, then it's called a represent. Then U is called a representation of the rotation group, right? Something which just reflects the group multiplication. But this kind of thing with an extra phase factor is called a projective representation. Okay, I think I've bothered you enough today, so I will stop now. But I will just end with one sentence, which is, sometimes, even if you have a projective representation, you can get rid of that extra phase factor by redefining the states. Remember, even when the states you're talking about can also change them by phase factors, right? Can't you? It's very often possible to get rid of this extra, although quantum mechanics allows you to have an extra phase factor in this description. Classical mechanics does not. Quantum mechanics does. Therefore, in quantum mechanics, there's this extra possibility that you could have an extra phase factor. But this phase factor can also be removed sometimes by changing the definition of what vector stands for which state. After all, you really have a ray, right? Or multiples of all vectors basically mean the same thing. So it's a ray which corresponds to a state. So instead of taking a particular vector from a ray, you could decide to take a different vector, essentially changing the phase factor there. And you may be able to do it in such a way that that absorbs out this factor. Okay. So such representations, we can get rid of the phase factor, are called trivially projective representations. They're projective representations. You have a phase factor, but you can get rid of them just by redefining your states. So that's a trivially projective representation. It's effectively a non-projective representation. And rotation group is one where such a thing can be done. So we are going to assume in the next class that this follows. UR1, R2 is UR1, UR2. And using this, specifically using this result, is U of, using just this, we are going to derive the basic commutation relations of the angular momentum operators. We have not even brought in the angular momentum operators, but I've said that often enough. Basically, they are the Lie algebra elements corresponding to this rotation group. So small SO3 elements. And so basically, you need to look at what happens close to the identity. We will talk about that in the next class. How to derive the angular momentum quantum relation, commutation relations. And in fact, you follow the same procedure, you can easily actually derive the Lorentz group commutation relations also by modifying the arguments slightly. In fact, the entire Poincare algebra can be derived in exactly the same way. So we are going to talk about that in the next class. Of course, next class is Monday, right? Friday is a holiday, isn't it?
Yes.
Yes, sir.
Okay, so we'll meet again on Monday, and we will talk about how to derive angular momentum quantum commutation relations in general, and then do the calculations for angular momentum algebra, the finding of the states, eigenstates, in a slightly different manner, which will be easily generalized to other cases as well. We've already done that. You know how to calculate, how to go from Jm to Jm minus 1 and so on. You know all this about J plus J minus operators, right?
Yes.
You know that, right? Standard angular momentum algebra treatment of eigenstates of J squared, Jz and so on. Why isn't there any response to that?
Oh, yes, sir.
You know that, right?
Yes, sir.
We are going to do that again, but in a slightly different way. For example, we are not going to assume the existence of a Casimir from the very beginning. You know what a Casimir is, I hope. But anyway, that is J square operator that is coming to J1, J2, J3. I will not necessarily need that. I will also not necessarily assume that the J's are Hermitian and still work with that. Still get the similar result with slight amount of more work. The reason why I'm doing that is that it actually helps to generalize to other cases as well. Okay, so see you on Monday.